And thank the organizer for inviting me. Although, yeah, when they invited me, I didn't quite I misread the title of the workshop. Okay, I just read 40 years of abstract interpretation. I forgot the next part. And so I thought it would be like, celebrating 40 years of great achievements. And as a great admirer of the work that's been done in this community, I could just say a few words and then some anecdotes, and nobody would notice that I'm definitely not an expert in abstract interpretation. And then I got another mail from Antoine saying, okay, so this is the next 40 years of abstract interpretation, and you have 45 minutes and you go first. All right? So I will do my best. Thank you. And I will start with an anecdote. So actually, like many people in this room, I discovered abstract interpretation by taking the course taught by Patrick and Radia. I think it was in 1989, and that was perhaps one of the first times they were offering it at ENS. I was an ENS student, and so all ENS students were in CS were encouraged to attend. They told us, no, it's a very new course, and there's no prerequisites. I had basically zero knowledge of programming language semantics at that time, and so I went, and it was tough. Yes, there was no prerequisites, but you had to absorb Hoare logic and Scott domains in 30 minutes each. And it went very fast, as you all know. And it was at an ungodly hour, like 8 a.m. on a Monday morning. So my main recollection is fighting, sleep and trying to stay awake and just absorb everything that was being flashed on the screen. Okay, and so afterwards I did a PhD in type systems. At least that was a little more accessible to me. And then, much later, I ended up doing static analysis, not very complicated ones, data flow analysis in the OCaml native code compiler. Later, when I worked on Java bytecode verification, and more recently, when I did the CompCert verified compiler, there's a bit of data flow analysis to support a few optimizations. And so, like every 5 years, I would have an epiphany, saying, "Oh, that's what Patrick and Radia meant." But oh my God, that's brilliant. So yeah, and it's also when working on static analysis that I discovered mechanized proofs. I started to do cog proofs basically at the same time I was doing Java bytecode verification. I had a verification algorithm I really wanted to trust. So that was tough, but that's how I discovered mechanized proof. And so I thought I would kind of combine both, and that's one of the projects I will describe briefly, and basically talk to you about both, so abstract interpretation and its mechanization. All right, so why mechanize abstract interpretation? There are two completely different reasons, orthogonal reasons. One is that static analyzers deserve formal verification. They participate in the construction of critical software, right? And so, like all other tools that participate in the production of critical software, this is my background screen, but okay, let me see if I can do something about that. I used to be in mirroring mode, but maybe I went out of it without noticing. View, presentation, okay, crossing fingers. Okay, not crossing fingers. Now it's mirroring again. Okay. Okay, wait a minute. Maybe I will unmirror and it will work better. Who knows? Shit. Where are the displays? Here. This is a great system, but you should ask people to... Oh, now it's unmirrored. It's unmirrored, but it's not showing anything. So, wait a minute, I have an idea. Okay, it's mirrored again. Cross fingers. All right, so yeah, I was saying static analyzers participate in the verification of critical software, and I think every tool that participates in the verification of critical software deserves some formal verification to build trust in them. And of course, abstract interpretation is a framework that guides the construction of static analyzers and their verification. Okay, just listen to me, okay? So that's motivation number one. And then there's motivation number two, which is that abstract interpretation is a beautiful theory. And it's a general trend these days towards mechanizing nice mathematics, okay? Just to, well, because it's a pleasure, because we may learn some new things or new way to present them. So maybe we will learn new things about AI. Go ahead. And it's also kind of a stress test for many proof assistants, as we will see. So, okay. Crossing fingers. So I'm not the first to say that it would be interesting. And so here are some previous attempts that I will mention. Okay. Yeah, we can try another adapter.
Does someone else have an adapter? No, I don't think so.
I've had some problems with this one actually, but not that one. So let's see.
Yeah, we just got like the same one.
Okay. Now it's not mirroring. Well. All right. So, oh, yeah, now I'm not going to see my slides. Well, never mind. Pretty good. Thank you. That's fine. Okay. So, so there have been several projects using COG or AGDA for the proof assistance, as far as I know. And the earlier one, as far as I know, was the master's internship of David Monio, who's somewhere in the room. And so that was back in 1998. And well, that was pretty brave. I mean, he set out to formalize, mechanize abstract domains and Galois connections, run into plenty of problems, and we'll see why pretty soon. And plus, at that time, the COG system was extremely primitive and hard to use. So you can read that David's irritation between the lines of his report. That's funny, but that's an interesting document. Then came the PhD thesis of David Pichardie, so 2002, 2005, advised by David Cachera and Thomas Jensen. So learning from the difficulties that David Monio had, he didn't set out to formalize the whole theory of abstract domain and Galois connections, but just some kind of gamma-only domains and proving only soundness, but also proving termination of analysis, fixed-point iteration. And the one application was an interval analysis for the Java card bytecode. And then, about 10 years later, we, with David and I and several others, we did the Verasco project, which was even less ambitious in terms of theory. It was gamma-only soundness, and we didn't even prove termination, but we wanted, we were pretty ambitious. We wanted to do something that looks like Astray with relational domains, etc. And I find it funny to see how theoretical ambition goes down as a function of time, while practical ambition goes up. And the workforce goes up immensely, you know, from a master's internship to a PhD thesis to a funded project with 3 PhDs and 5 labs. And then the more recent work, which go back to the PhD thesis format, is the one of David Darais, advised by David Van Horn, which presents a kind of a new kind of Galois connection, or a special kind of Galois connection that they call constructive Galois connections with application to gradual typing. And I'll try to discuss a little bit David Darais' approach at the end, but let me start with a quick recap on Project Verasco. So it's the verification of a static analyzer for C that is based on abstract interpretation, that is written and proved correct in COG, and that kind of connects to the concert compiler. So that involves 3 PhD students, Jacques-Henri Jourdan, Vincent Limporte, Alexis Fouillet, and then a number of scientists, several of whom are in the room. And the PI was David Pichardie for the static analysis part. So as I said, the goal was to develop and verify in Coq a realistic static analyzer by abstract interpretation. So we wanted to analyze a COMSERT subset of C, which is a pretty large subset. We wanted to have non-trivial abstract domains, including relational domains. We still admire the modular architecture of Astray, so we tried to reproduce that. And we wanted to have Coq proofs of soundness against the COMSERT operational semantics. And if you need a slogan, so COMSERT, for me, it was like 1/10 of GCC in terms of quality of code, number of optimizations, etc., number of features implemented, but formally verified. And maybe one of the goals of Verasco was 1/10 of Astray, but formally verified. Okay. I'm not sure we reached the 1/10 bar, but we'll see. So basically, that's the architecture and the main components. So at the top, you have the COMSERT compiler that kind of pre-processes your source into an intermediate language called C# minor, and that's where we chose to plug the abstract interpreter, which basically analyzes all paths of control, of course, and reports alarms. Okay, and is parameterized by a state abstraction, which abstracts over memory states and over pointers, and is parameterized over a numerical domain, which is a combination, a channel-based combination of a bunch of domains. So there are non-relational domains like integer intervals, floating point intervals, integer congruencies, wrapped into a relational interface systematically. So these are functors. Typically, those boxes are functors in terms of ML and Coq modules. And then we also have some relational domains, like the domain of octagons, implemented by Jacques-Henri Jourdan and proved correct from scratch and without matrices, which is quite an achievement. There's the domain of symbolic equalities, and then there's the domain of convex polyhedra, so a linear equation that was developed at Verimag, and it's the only one that uses validation a posteriori. So there's an oracle that does a lot of operations and produces FARCAS certificates, and those are checked by a verified checker. Okay, and I think I mentioned all the boxes. Oh yeah, and this one. So here we use mathematical integers, and at the very end we do modulo 2 to the 32 or 2 to the 64 integers. It's easier this way. Okay, so I'm not going to go over all of this, just give you a glimpse of some of the interfaces used. So what's a generic interface for a numerical domain? For a non-relational domain, there's what is a generic mechanized interface for a numerical domain. So there's a presentation that is pretty popular these days. So it's the gamma presentation used by Pichardie, but also used by Berthaud in course notes, by Nipkow and Klein in their textbook. So basically, you have a semi-lattice of abstract values, a concretization relation, gamma, from abstract values to sets of numbers, some forward abstract operators with a soundness property, and backward abstract operators to refine conditionals. Okay, so this is pretty standard and pretty easy to formalize in Coq. But when we started Verasco, it was not completely clear what a generic interface for a relational domain was. And we settled on this approach. So there are 3 major operations: assign, forget, and assume, that change the abstract value. Assign reflects the effect of setting a variable to some simple expression built over variables and constants. Forget is for just non-deterministic assignment to a variable, and assume whether a Boolean expression is true or false. And we found that out later that, to report alarms and also to communicate with other domains, it's good to have queries like is x less than y, or x mod 4 is 0, and that can be actually expressed as getting a variation interval for an expression. Okay, as tight as possible. If it's only one element, for instance, we have an answer to x mod 4 equals 0. And there's also another query, which is whether the expression is always well defined or can go wrong. Okay, and that gives this piece of coq code, this coq declaration. So it's a class which is basically a record type on steroids, but it's a dependent record type, so it contains a bunch of operations on the abstract values, type T, like the top, the join, widening operator, and those forget, assign, assume operations, and non-block and get interval queries. And then the second half is the specification. Okay, so you can also put properties in those records, theorems, and the specifications are phrased in terms of gamma, as I said. So function from T to sets of environments, okay, variables to numerical values. And here's the specification. So LEB is sound, the top is the greatest element, join is sound, forget is, etc. So I will not read all of that. Just point out that it's pretty readable, okay, with a little bit of Unicode notations, and not very long. Okay. A few words about the abstract interpreter for the C# minor language. So it's a little bit complicated because C# minor is like C. It has a complicated control flow. So a statement can exit normally or early by an exit, which is a generalization of break and continue, or early by a return, or early by a goto. We handle gotos. And it can be entered normally or entered by a goto, searching from a label. So that's a complicated flow of control, and each of these flows corresponds to some bits of abstract state. Okay, so this is the abstract state when we enter normally. Here we have a mapping from labels to abstract states, and the interpreter either returns an alarm or abstract states for all the possible outputs. So it's structural abstract interpretation defined by recursion over the statement. We use a local fixed point iteration for every loop, a global iteration for gotos, and we expand all functions at point of call. So pretty simple. And the proof, actually we took inspiration from Yves Berthaud's course notes. So it's possible to prove the soundness of this interpreter straight from the semantics, operational semantics, but it's a bit of a pain to keep track of all those abstract states and control flows. So we did that in 2 steps using a Hoare logic as an intermediary. Okay, so basically we have a little Hoare logic for C# minor, which has 1, 2, 3, 4, 5, 6. It's a 7 tuple Hoare logic because there's 2 preconditions and 4 postconditions. And it's easily proved correct with respect to the small step operational semantics of C# minor. And then we prove that basically the abstract interpreter produces, if it doesn't report an alarm, it produces a valid weak 7 tuple, okay, where you just interpret, you use gammas to go from abstract state to preconditions and postconditions. So it's kind of trivial, but it really simplifies things, and then it lets us do more clever things in the interpreter, like unrolling loops sometimes. No. Okay, and so in practice, so Verasco works. So the soundness was fully proved, 30,000 lines of code. We get an executable analyzer by Coq's extraction from production of vocaml code from Coq code. It is able to show the absence of runtime errors in small but non-trivial C programs, but it also needs a lot of improvement. As I said, well, some loops actually need manual unrolling or unrolling annotations. Otherwise, we are not able to show, for instance, that an array is fully initialized at the end of a loop. And that probably comes from our memory abstraction, which is neither precise nor efficient. And as a consequence, the analysis is pretty slow, up to 1 minute for 100 lines of code. So this is not going to put Astray out of business, but I think it was encouraging, okay? And then the project kind of stopped because I guess there's not that much interest in informally verified static analyzers after all. But still, so it is publicly available, and I think for some of the techniques that we have, we and Mopsa are perhaps the only 2 open source implementations available. So, pardon me? And I don't know, do they do the channel-based communication, for instance, or some of those very Astray-like things we try to imitate? I'm not sure. So anyway, so I think Verasco also has a bit of a value as a kind of documentation, let's say, or simple implementation of some of those ideas.
How can it be at 30,000 lines?
You mean?
That's a big number.
Oh, no, that's pretty small. Well, I cannot give you a breakdown between specification, code, and proofs. I think some algorithms here are pretty subtle. Just a good integer interval analysis is already a lot of code because there's plenty of cases to consider. Okay.
All of these are covered by the 30.
Oh, yes, absolutely. Oh, no, it's not just, the abstract interpreter itself is maybe, I don't know, 500 lines of code and 1,000 lines of proof. That's pretty easy. No, I think that the difficulty is really in all those numerical stuff. Okay.
Why was so slow? Can you comment?
No, actually, I don't know. Well, I don't know. Again, I think the memory abstraction was pretty inefficient, but I can't really give you the details. And as you know, when you get less precise, you also increase analysis times. Okay, you start iterating over huge sets. So that's probably what hit us. Okay. All right. So, but yeah, coming back to what we achieved. So we proved soundness, but we proved nothing else, and that's a little bit disappointing compared with some of the holy texts that I deeply respect, like Patrick's notes at Mark Tuverdov, the calculational design of a generic abstract interpreter. So we have no Galois connections. We have gamma-only domains, but no alphas, which means no optimality guarantees. We don't try to prove that least upper bounds are least upper bounds, just that they are upper bounds. We all our abstract operators can over-approximate, okay? And that's what let us do translation validation for some of them, okay, verification a posteriori. They produce certificates of soundness, but not of optimality. There's no guarantees on the termination of fixed point iteration, so we use fuel. We jump to top after a huge number of iterations, which means that in practice we diverge. There's no proper collecting semantics of the kind that Patrick would find acceptable. And there's no calculations. Everything was kind of implemented, coded, saying, okay, it looks good, and now let's prove it sound. It was absolutely not derived systematically, and I will come back to that later. So all that was a good match for Coq's constructive logic, but well, we were punished by many tops during the development. I mean, it's very easy to miss a case and return top where actually you could have returned something better. And that's awfully hard to debug, as people who write abstract static analyzers probably know. And it was also slightly disappointing. I think in particular, David Pichardie would have loved to stay a little closer to the orthodox presentation of abstract interpretation. So let's see what we can do, or what has been achieved. Can we mechanize abstract interpretation by the book? Okay, so Galois connections and the calculational style. Well, as you know, this is a classic Galois connection. So here I'm using sets of concrete values as one of the domains, and then abstract things like intervals as the abstract domains. And so there's this beautiful adjunction property that connects the abstraction function alpha and the concretization function gamma. And one of the great things you can do with that is to calculate sound and optimal abstract operations. You can even calculate program logics, like we saw yesterday, but let me just stick with abstract operations. So if you have an operator from concrete values to concrete values f, then you just write this equation, extend it to sets, compose it with alpha and gamma, and that gives you an abstract operator, f sharp, that goes from abstract values to abstract values, that is sound. So if C is in the concretization of A, then f of C in the concretization of f sharp of A, and that is optimal. So f sharp of A is the smallest abstract value that has that property, and can be calculated systematically. So my calculations don't look as good as Patrick's, but so let's say what's the abstract successor operation in the domain of parity, where you start to write it's the alpha of the set x plus 1, where x is in the concretization of A, And then you unroll some definitions and invoke some general properties of Galois connections, and maybe at some point you do a case distinction, and then you do more good reasons, and you get your abstract operator appears as a 4-case function, just like Venus rising out of the sea, and it's just beautiful. It's beautiful, it's sound, and it's optimal. Hey. What's the problem when trying to mechanize that? Well, the problem with alphas. First, they are sometimes not well defined. Like if you have rational intervals, this set has no alpha. There's no tightest interval that approximates the interval minus square root of 2. That was a big disappointment when I realized that. Probably I was sleeping when they mentioned it in the lecture. And so I realized like 12 or 15 years later that alpha doesn't always exist. And it felt like, the Santa Claus doesn't always exist. It was, I was really heartbroken. So, but let's say alpha is well defined mathematically. It is generally not computable. As you know, as soon as your concrete domain is infinite, you end up enumerating infinite sets, and it's game over. For instance, for intervals, the alpha of a set of integers or numbers is the infimum and the supremum of the set, and if the set is infinite, of course, infimum and supremum are not computable. Just being able to compute whether a set of intervals has an upper bound or not would solve the halting problem and pretty much all problems in computability theory. So, of course, a computable alpha can only look at a finite number of elements of the set S. Okay. And why is that a problem? It's that because most proof assistants, or at least those that I know, are logics of computable functions, as Milner's put it, LCF. They vary a lot in their support for classical logic, like Agda is purely constructive, Hall 4, Isabelle Hall are fully classical, Koch and Lean are kind of in between constructive, but it's okay to add classical axioms like excluded Milo. But they are all pretty strict when it comes to functions. And having computable functions is great. That supports computation within the prover, extraction to efficient functional code. And of course, you can always add axioms to define non-computable functions. The axioms of description, which are like similar to the axiom of choice, which also gives you the existence of a magic function f. Okay, but again, this tends to break executability in the prover and the ability to extract code. So it's frowned upon. And as we'll see, it doesn't really help actually for the alpha. Okay, so there was a plan B, which is Pichardie's approach, which is no calculation and gamma only, but you can do optimality proofs using gammas only. Okay, so you lose calculations. You need to define your abstract operators F# a priori, or calculate them on paper, and then transcribe them in the proof assistant. You need to prove soundness. But optionally, you can prove optimality just with gammas. Okay, it's just a little bit of a pain, and it works. But some elegance is lost compared with the calculational approach. Now there's a plan M. M is like monads, and that's the Darais and Van Horn constructive Galois connections I wanted to talk to you about. And it starts with an observation. I don't know if everyone is familiar with monads. So basically, monads, it's a trick to have to add input-output and other effectful computations to a pure functional language, like Haskell, or just the pure lambda calculus, right? And the idea is that you will have a type, M of A, which is a type of effectful computations that end up producing a value of type A. And for instance, print in the IO monad would be a string to M unit. So it takes a string, it prints it, and it returns the trivial value unit. And then you can combine those monadic computations using ret, which injects a value as a trivial computation, and bind that sequences two monadic computations. And the important thing is that there's no projection. From a monadic value in general, M of A, monadic computation, there's no way to just extract the value and treat that as a pure computation, basically. And the observation of Darais and Van Horn in 2016, and they were working in AGDA at the time, is that we could use a monad to separate computable functions such as f sharp, which the abstract operator in the end must be computable, and that can only use constructive logic, and separate that from non-computable functions such as alpha, which will live in a world they call the specification monad, where you can also use classical logic if you want. And the separation would guarantee that in the end, your F-sharp you compute would be free of specification effects. And for that, you just write as this. So ret of sub sharp of alpha of A. So this must be a pure value, right? So and ret turns it into monadic computation. And to the left, you have the equation involving alpha, which is in the monadic world. And then you calculate, and you can even use monad laws if you want, in addition to everything else. And if you manage to put that in a form ret of a pure expression, then you win. Okay, then sub sharp of A is this pure expression. So that's a very simplified account of their paper. So and again some more details, but again still pretty much simplified. So the idea is to start with two functions that are constructive. So there's interpretation, which takes an A, an abstract value, and returns a set of concrete values, as usual. And then there's extraction, which applies to a single concrete value, not a set of concrete values, just a single concrete values, and should produce an abstraction. A key observation is that this extraction must be computable. For instance, if you need to abstract constants, you are analyzing expressions, and you have constants, you need to have something like nu to find the abstract value corresponding to each constant. Okay, and so from there they derive a Galois connection of a particular shape that I didn't know. So it's between sets of concrete things and sets of abstract things. So for instance, for the even odd parity domain, that would be subsets of even and odd. Okay, why not? But I don't see how intervals fit in that, so I'm a little bit uneasy, but never mind. So you can define alphas and gammas in the trivial way, and as a monad they use the classical infinite non-computable sets, functions from X to prop, basically the membership function of the set. As opposed to computable finite sets of A's, lists of A's, for instance, which are the arguments and the results of abstract operators. And maybe it's a little too small, but so that's taken from their paper. So to the left, you have a calculation on paper in their monad, in their domain, sorry. And to the right, you have the same calculation that's being mechanized in AGDA. So that's really a tour de force, as we say in French, because AGDA has no interactive proof mode, but they actually implemented one. So what you see is pretty small on the right, the do, the brackets, the curvy brackets, etc. These are all terms, AGDA terms, that explain how to refocus and unfold and apply simplification rules and so on. So this is completely crazy, if you want my opinion. But, no, not crazy, black magic. This is black magic. Okay, but in the end it works, and it looks a little bit like the original on-paper derivation. Okay, and if I have 5 more minutes, then the plan M can be turned into a plan U like universes. So in a system like Cog, so you can use monads. Remember, the original motivation for monad was to separate effectful computations from pure computations, but in some other languages, you do that with a type system. Okay, for instance, in Java, there's throws clauses and methods. If it's there, it means a method can throw exceptions, and if it's not, then it cannot. And in Cog and Lean, there's something a little bit like that. In their universe structure, the universes are types for types. And so they have two major universes, prop, which is a universe of logical propositions, and then that can have proofs, and type, which is a universe of data types and their computations. And various combinations are possible. This is very simplified. Various combinations are possible, but there's something very important, which is that a computation in type cannot depend on a proof in prop. And for instance, if you have a proof of this Turing machine terminates or it does not terminate, which you can get with an axiom, classical axiom, for instance, We can reason by case whether the Turing machine terminates or not, which is very useful, but we cannot define a Boolean values, it terminates, where you give it the proof and the Turing machine the proof and it says yes or no. Actually, all functions that have this type are constant, okay, because they cannot, the bool, which is in type, cannot depend on this proof, which is in prop. And the good thing about this distinction is it makes it possible to add excluded middle or other classical axioms without endangering extractions. Extraction that erases everything that is in prop. Okay, so that's pretty cool. And so if we want to do the plan U in code, so I tried to do that while preparing those slides. So we can define alpha as a relation between sets of concrete things and abstract things A. So this is the parity abstraction, so there will be 4 cases, bottom, even, odd, and top. And it's just a relation, okay, nothing is computable in there. You can show that it satisfies the adjunction property, so it's a good alpha, if you want. You could say, okay, let me use a choice axiom or a description axiom to get an actual alpha function from this predicate, but actually it leads nowhere, and it can endanger extraction. So let's not do that. Let's stay with relations. You can describe abstract operators with the help of isAlpha. So this is slightly tricky, but the idea is to show that for any A, which is the abstraction of the argument, there exists in type an A prime, so we can actually construct an A prime that satisfies this property. A prime is the alpha of the set of the image of gamma of A by the successor function. Okay? So this is the closest I could get to the equation. So sharp equals alpha suc gamma. And now you can use interactive proof mode to construct A prime. And now, in the end, you can project out the abstract operator and its soundness and optimality proof as the 2 components of this kind of dependent product. So it's not super pretty, so this is the proof, the derivation for successor. Of course, there are 4 cases, but top, even, and odd. And in each case, so either I just invoke theorems and the corresponding value, but top, pops out of the theorem, or I actually say it explicitly. Okay, so it's not super pretty, but it's a step, let's say, towards some kind of calculation. So as I say, it's kind of a Pyrrhic victory for mechanization. So in the end, it is possible to mechanize some forms of Galois connections. That could be Darais and Van Horn's eta mu, or the is alpha gamma presentation, as I just showed you. Use that to calculate abstract operations, but the mechanized approaches don't have yet the crispness nor the immediacy of the classic pencil and paper presentation of AI. So what's next? This is the next 40 years, after all. And I'm not sure I have much to say there, but a little bit. So coming back to the first half of my talk, the formal verification of static analyzers, I think this naive, gamma-only abstract interpretation provides a robust approach. Okay, all you want to do is prove the soundness of a static analyzer. That will work fine. That's now textbook material. I mentioned the concrete semantics book. It scales to non-trivial analyses, including relational analyses, as we demonstrated in Verasco. It's perhaps hard to scale much further because algorithms get extremely complex. I don't know if Jérôme Ferret is here. We briefly looked with him at filter domains and then ran away. It was just too hard. And as I said, there's not that much interest actually for verified static analysis outside of compilers. And now on the mechanization of abstract interpretation, as I showed, it's still a challenge for contemporary proof assistants. And that's actually interesting. I believe abstract interpretation is deeply grounded in set theory. So it's not just that Patrick and Radia liked modern mathematics in the 1970s. I think there is something deeply set theoretic, just like there is something deeply order theoretic in Scott domains. Okay, I can't quite put my finger on it, but there is something set theoretic. It's not just a 1970s fashion. Yet, at the end, it produces algorithms, and that's where things clash, basically, and that's where it becomes interesting. And then contemporary proof assistants have poor support for the calculational style. And it's not just for Patrick's derivation, it's also for Richard Bird style program derivations, for instance. It's also for undergraduate mathematics, okay, when you do equal blah, 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 equal blah, 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 equal blah, blah, blah. So there's probably something to do there independently of abstract interpretation. All right, and so just to conclude, that was the first 40 years. Now, the next 40 years. Actually, this morning, I took the tube, and I saw also there's you can extend to 160 years if you want. Thank you.
So we have time for a couple of questions.
Yeah.
Yes, David.
So you mentioned certificates of correctness for certain abstract domains. At some point, we investigated certificates of optimality, but then people lost interest. It was difficult to find students. This would mean that the interpreter would be partially correct because it could fail to show. It would be partially optimal. You would have to put everything in a Mona or something like that. What do you think about that?
I think it's generally useful. The VPL, your Verimac polyhedral library, we try to use it in other projects where actually having optimal results would have been good. Proofs of optimality would have been good. So I think it is great in general. And the possibility of failure during analysis, I think it's not too serious. I mean, at least the user knows what's going on. Okay. But practically, it's not that much different from just returning top and then making alarms. Well, it's a little better, let's say. It's an alarm with a better diagnostic. The problem is probably not in your code, but it is in the analyzer. Patrick.
Yeah, when I do my computation by hand, I think to make Maple style of thing. And I was wondering, would it be possible to have a tool which is both Maple and Cog, that is where it's essentially rewriting, and at some point you have to have a proof, which is a bit more difficult, but most is rewriting and things like that.
Okay. So you can do proofs by rewriting in Cog. It's certainly less convenient than in Maple or systems like this. And but yeah, there's a growing interest towards formalizing like undergraduate mathematics in Cog, so they will have to provide a more Maple-like experience. There's no way around that. But yeah, Cog and those systems are more oriented toward deductive proofs. Yes.
My understanding of how people work in Coq is or some will, based on software foundation, is that you'll often define what I'd call a procedure, and they would call a function, and then a relational counterpart to it.
Yes.
And then you work to kind of show the two together. Are there, in general, techniques for just starting with relations and then somehow turning to something that's extractable as a procedure without having to do the work by hand?
That's an interesting question. I don't know of any off the top of my head, but this is such a natural thing to have that probably someone has looked into this. So let's discuss that at the break. Mouli.
I have two questions.
Oh, not sure we have the time budget.
It's more problematic. In the work of concept interpretation, usually, especially in pointer analysis, every time I try to prove an algorithm to be sound, I found a bug.
Okay.
And it's including references in my own, unfortunately. So when does this happen to you? In this proof, you are finding also bugs?
Oh, I'm pretty sure. Well, so my experience is just with the data flow analysis of CompSert, but yeah, I found a bunch of corner cases, and as you say, it's not so much with numerical abstractions, but very much with pointer and memory state abstractions. Those can be super tricky, especially with the CompSert memory model, a concrete model, which is not trivial. Either it's not just a mapping from locations to values. So yes. When you try to prove things, you find bugs. That is true. But maybe not very serious ones or bugs you don't often run into. But that's also why it's good to test and to prove at the same time.
And you fix them.
Of course. In the end, there's no admitted or whatever in the 30,000 lines in the end.
The second one,
Second question.
more technical. I love the calculational one, but I'm trying to understand in the work that John Herbst and Dennis Copan and Greta and I did. I don't know if you know this connection, alpha from below, alpha from above. So your work seems to be what we call alpha from below. Do you know the difference? So we connect calculational, connect logic, classical logic to absolute interpretation. Theory formulated in logic to absolute interpretation.
Okay.
And the idea is we have two mechanisms. One is that you iterate from bottom, and the other one is you iterate from top.
Okay.
You only iterate from bottom.
Yes. We do only iterations from bottom. Then that is correct.
Does it make sense for you also? Because we find in
That's an excellent question. Actually, I don't think we discussed that during the project, but okay. So yeah, we didn't think of that. So I won't be able to answer your question. All right.
Thank you very much.
Thank you.